All right, so let's do some examples of working with logarithms. And in particular, what we're going to work on is expansion and contraction of logarithmic expressions. So example 1, we're going to expand the natural log of x plus 1 squared times x plus 2 to the third over x plus 3. And the rules that we're going to use to do that are going to be that the natural log of AB is equal to the natural log of A plus log B, that the log of A over B is equal to log A minus log B, and that the log of A to the R is equal to R log A, as long as R is a rational number. Okay, so we're going to use that to attack this expansion problem. The natural log of x plus 1 squared x plus 2 to the third over x plus 3, I notice in here that I have this product on the top, and I've got a quotient on the bottom. So one way of attacking this thing would be to say, let's deal with the quotient first. You don't have to do this step by step, but I'm going to in this case. So this is going to be equal to the natural log of the numerator minus the natural log of the denominator. Now I've got a product in here, so I can apply rule 1. So this is the natural log of x plus 1 squared plus the natural log of x plus 2 to the third minus the natural log of x plus 3. And now I've got these powers inside the log, which means I can use rule 3 to pull those powers out front. And that gets me 2 times the natural log of x plus 1 plus 3 times the natural log of x plus 2 minus the natural log of x plus 3. So this is expanded fully. Okay. If I was doing calculus and I want to take a derivative, this is exactly what I'd want to do here. I want to have the expression built all the way down to this, because at this point, taking the derivative is a very simple chain rule, as opposed to if I'm working up here and I want to take a derivative of this, nasty bastard, I'd have to do 1 over this, and then the derivative of this entire expression on the inside, which would be some enormous pile of quotient and product rules. So we want to avoid that when we can. Okay, so now let's do a logarithmic differentiation. So suppose that I had y is equal to the square root of x times x squared plus 3 over x minus 2. And I want to find dy dx. So step 1 is to write it as a logarithmic expression. So step 1, log y is equal to the natural log of the square root of x, x squared plus 3 over x minus 2. Step 2 is to expand. So I'm going to take this logarithmic expression and I'm going to write it out in an expanded form. That's going to get me the natural log of y is equal to the natural log of the square root of x plus the natural log of x squared plus 3 minus the natural log of x minus 2. I have to check and make sure that there's not exponents in there that need to come out. And it might not look like I've got one, but there's one right here because root x is really x to the 1/2. So if I want to finish my expansion, I have to write 1/2 times the natural log of x plus the natural log of x squared plus 3 minus the natural log of x minus 2. And I can't really do much with this square right here because it's not all by itself. Remember, the rule says that the natural log of a to the r is r log a. So the entire interior needs to be raised to a power in order to pull that power out. Another pitfall that people get into sometimes is they think, oh, well, I've got this sort of expression right here where I've got a sum. Can't I split that up? But remember, the log takes products into sums. So if you have a product of functions, you can split it into 2 different logs. But if you've got a log of a sum, it's stuck. There's nothing you can do. Step 3 is we're going to use implicit differentiation. So what that's going to get me is 1 over y dy dx on the left-hand side. And on the right-hand side, I'm going to get 1/2 times 1 over x plus 2x over x squared plus 3 minus 1 over x minus 2. Because the derivatives of the logs by the chain rule are just 1 over u times u prime. So this guy is almost complete. So let's finish it. Step 4, solve for dy dx. So dy dx is equal to y times 1/2 1 over x plus 2x over x squared plus 3 minus 1 over x minus 2. But I know what y was, right? Y is right here. So I can just grab this, and I can put it right here. That's y. And this is done. You've found dy dx as a function of x. So the last example that we're going to do is going to involve taking a derivative of a natural log with a complicated expression inside and showing another one of the trigonometric rules for integration and differentiation. So let's compute d by dx of the natural log of the absolute value of the sine of x. Remember that the chain rule says that the derivative of f of u is equal to f prime of u times u prime. So this is going to turn into 1 over the sine of x. The absolute values got disappeared here because remember the derivative of the absolute value of x, derivative of the log of the absolute value of x was equal to 1 over x, times the derivative of the sine, which is minus the cosine. But minus the cosine over the sine is minus the cotangent. And so you've just discovered, or we have just discovered, another one of the rules for differentiating and integrating. The integral of the cotangent must be the natural log of the sine of x with a negative sign in front, because the derivative of the natural log of the sine was negative cotangent. All right, so the exercises in this section are going to be largely computational to get you used to the rules of logs or to remind you how the computational rules of logs work. The really high-powered technique here is the logarithmic differentiation, which I encourage you to practice. And I'll see you next time for e. Where did e come from? What's the exponential function? How does e enter the picture that we've drawn here? That's what you find out in the sequel.